So in this video, we'll do another example of finding the slope of a curve at a point. And the equation in question is an implicit function. It's not going to be really feasible or even possible to get y by itself, to solve for y and then find the derivative. So the equation is this one, 10x to the fifth power times y to the eighth power equals 3y plus 7. So I'm going to get started by applying the derivative to both sides of the equation, d dx of 10x to the fifth y to the eighth equals d dx of 3x plus 7. Oops. So the right hand side is going to be relatively easy. Oh, I made a mistake. 3y plus 7, not x. 3y. 3y plus 7. Okay. The right hand side will be relatively straightforward. Left hand side, not so much, because we're going to have to use the product rule. Now, the first thing I'm going to do is, I guess I'll group the 10 with the x to the fifth power. If I wanted, I could first move the 10 out front. That it doesn't really matter. I'll group it with the x to the fifth power. We'll just go from there. It shouldn't really matter that much. So I'm going to apply the product rule. I have some function of x times some other function of x, and we're finding their derivative, so I need to use the product rule. So this will be d dx of 10x to the fifth times y to the eighth power plus 10x to the fifth times d dx of y to the eighth power. Okay. Now on the right, I'm just going to go ahead and apply the chain rule. If we had an x here instead of a y, the derivative would be 3, right? The derivative of 3 times some variable plus 7 is 3. But then because of the chain rule, I have to then multiply by dy dx. So this will be 3 times dy dx. Okay. So the right-hand side, not so bad. Left-hand side, we have still a bit more work to do. So for this factor in the first term, the derivative is not that hard, and the reason is that the variable with respect to which we are finding the derivative is the same as the variable in the expression. So we just apply the power rule, we'll get 50x to the fourth power, no big deal. In this factor of this term, however, we have to apply the power rule, sure, because of the 8, but since the variable with which we are finding the derivative, with respect to which I should say we are finding the derivative, is not the same as the variable in the expression. So I have to be a little more careful. I have to apply the chain rule, basically. So this will be 50 x to the fourth, as I said, times y to the eighth plus 10x to the fifth times 8 y to the seventh, that's the power rule. I'm finding the derivative of the outside function, times dy dx, the derivative of the inside function, y being the inside function. That equals, of course, 3 times dy dx. Okay? So the calculus part is done. Now starts the algebra phase, and it looks complicated, but I want to remind you, this is kind of like having 7 plus 9a equals 3a. Something like that. It's just a linear equation. It's not really that bad. Obviously, we have so many more symbols here, but they're just going to get moved around in the algebra. We don't have to really deal with the x's and the y's. We just have to move them around. We don't need to. We're not solving for x. We're not solving for y, basically. We did not undo that just yet. So if this is the equation I indeed had, I would start by subtracting 9a on both sides to move that 9a to the right-hand side. Well, the analogous term is this whole term. So I'm going to subtract this on both sides to move it to the right-hand side. The 10x to the fifth times 8x to the 8y to the seventh times dy dx. So I'm going to subtract 80 x to the fifth, y to the seventh, dy dx on both sides. This term will just sit where it is. So 50 x to the fourth, y to the eighth equals 3 times dy dx minus 80 x to the fifth, y to the seventh times dy dx. And as we've done in previous examples, we have a common factor here. Dy dx is a factor in both terms on the right-hand side, so I need to factor it out, and I'm going to put what's left over in parentheses. Okay, and then both of those dy dx's will come out to the right. They could go to the left, it doesn't matter. I could put them in front of everything or in back of everything. That doesn't matter. I'm going to choose to put them in the back. So this is 50 x to the 4th, y to the 8th equals 3 minus 80 x to the 5th, y to the 7th times dy dx. And now I'm almost done. You can probably guess what's going to happen next. You pause the video and think about it for a second. I need to divide both sides by this factor so I can get dy dx by itself. So this will be 50 x to the 4th, y to the 8th over 3 minus 80 x to the 5th, y to the 7th equals dy dx. So I found the derivative of that implicit function. Okay. Now we're not quite done, because what we really want to do is find the slope at the point 1, 1. Okay. So dy dx at the point 1, 1. In a future video, when we do another example like this, I'll make sure that I'm not using 1, 1, the same number for both x and y. It turned out for these equations that was convenient, but it's not always going to be like that. So this 1 needs to go in for x in both of these places, and this 1 being, they're both 1, but they're there for different reasons. One is x, one is y, needs to go in for y. So basically that means my numerator is 50. 50 times 1 times 1. My denominator will be 3 minus 80 times 1 times 1. So was that negative 77, I believe? So this equals 50 over 3 minus 80, or 50 over negative 77, or if I want, negative 50 over 77. And if we needed a decimal version of that number, we could do that, but we're just finding the slope. That's all we really needed. So this is the slope of that curve at the ordered pair 1, 1.